In this video, we are looking at a few proofs involving divisibility. Let's first talk about the idea of divisibility. When we say one integer is divisible by another, what exactly do we mean? Well, I'm going to give you an example. Let's take a look at the number 30. If I ask you, is 30 divisible by the number 3? What would you say? Well, a lot of students will take 30 and divide it by 3 and see what they end up with. If we do this, 30 divided by 3, we get 10, meaning 3 goes into 30 a total of 10 times. We have no decimals here, we have no remainders. This means 3 is actually a factor of 30. So we could write 30 as a product, 3 times 10. If 3 is one of the factors of 30, we can write formally 3 is a divisor of 30. And in the same breath, 10 will then also be a divisor of 30 because 10 goes into 30 a total of 3 times. Here's the formal definition that we are going to use in the video. If we have any two integers, let's say C and D, and we say that D is not equal to 0, because remember we don't want to divide by 0 ever, we can write that D is a divisor of C if C is equal to DK. What does this mean? Well, first of all, D is a divisor of C. This is the notation we use. That vertical bar reads is a divisor of. So D is a divisor of C if we have the following. If we can write C as a product where D is one of the factors. So here D is a factor of C, where the other factor is also an integer. Then we say D divides C. So in our example of the 30, we saw that we could write 30 as a product, 3 times 10. And so from this, because both of these are integers, we could deduce that 3 is a divisor of 30, as well as 10 is a divisor of 30. We could also write it as a different product of factors. So we could say 30 is the same as 15 times 2. Because both of these are integers, again, we can use the same argument to say, well, 15 will then go into 30, or 15 will be a divisor of 30, and 2 will be a divisor of 30. And we can even look at the extremes. We can write 30 as a product, 1 times 30. Both of these are integers, so 1 will always be a divisor of 30, as well as 30 itself. 30 will always go into 30 exactly once. All right, so let's do our first proof. The statement says, let A, B, and C be any integers. A is not equal to 0 and B is not equal to 0. If A is a divisor of B and B is a divisor of C, then A will also be a divisor of C. We are going to do a direct proof for this result, meaning we are going to assume the hypothesis A divides B and B divides C, and then we are going to try and prove that A divides C. When we do our proof, we always state all of the obvious facts, even though it feels like repetition. We are going to set the scene and say let A, B, and C be integers, where A is not equal to 0 and B is not equal to 0. And we are going to assume the hypothesis. So we are going to assume A is a divisor of B and B is a divisor of C. Our assumption is out of the way. Now we are going to use the definition to show what this assumption means. If A is a divisor of B, we saw that we can write B as a product of two integers where A is one of them. So we can write B as a product A times M, where M is some integer. It simply means A is one of the factors of B. The second assumption, B is a divisor of C, means we can write C as a product, where B is one of the factors. Now, just to be as general as possible, we are going to say that C is a product Bn, where n is an integer, just so it has nothing to do with the first assumption. All right, so the first one says A is a factor of B. The second one says B is a factor of C. And now we would like to see, can we describe C as a product? What would we like to prove? Let's just go back to that. We would like to write C as a product of integers where A is one of the factors. Let's see if we can do that using our assumption. Well, we know that C is equal to Bn. And we also have an expression for B. We've said B is equal to Am. So we can substitute this into our expression for C. We would like to show that A is one of the factors, and there it is. So if we just rewrite this slightly, and we say C is equal to A times Mn, we can do this because of the associative property of integers, right? We have that C can be written as a product where A is one of the factors, and the other factor involved, Mn, is an integer. This means, or we can conclude, this means that A does divide C, and our proof is complete. Let's take a look at another statement. This one says if we have four integers, A, B, C, and D, where A is not equal to 0 and B is not equal to 0, and if we have that A divides C and B divides D, then the product AB will be a divisor of the product CD. We're going to do a direct proof again. So we are going to start by assuming the hypothesis. We will assume this part is true, and we are going to prove that this part, AB is a divisor of CD, is true. So let's set up our proof, and again, state everything that's obvious. Let A, B, C, and D be integers. A is not equal to 0, B is not equal to 0, and let's make our assumption. Let's assume A is a divisor of C and B is a divisor of D. Again, this is our assumption. This is us setting the scene for the proof, but we have to expand on what it means if A is a divisor of C and B is a divisor of D. So this means, let's just elaborate using our definition. It means C can be written as a product where A is one of the factors. So again, let's say C is equal to AM, where M is some integer, and D can be written as a product where one of the factors is B. And again, just to be as general as possible, we use a different integer here. And let's say this is N. This is what we have to work with. This is our assumption. What do we need to prove? We need to prove that AB is a divisor of CD. So our focus is going to be, can we describe CD as a product where AB is one of the factors? Okay, so let's start there. What will CD be equal to? We have something that describes C. C is equal to AM. And we have something that describes D. D is equal to Bn. Again, we can use the properties of integers here. We can rewrite this. Commutativity says the order in which we multiply is not important. Associativity says we can associate certain or group together certain integers or factors without changing the meaning. We would like to show that AB is one of the factors. So let's group together AB and everything else that remains, Mn. So here we can write AB as one of the factors, and the other factor, Mn, since M is an integer and N is an integer, the product will be an integer as well. Once we can do this, once we can show that AB is a factor of CD, we can write AB is a divisor of CD, which is exactly what we exactly what we wanted to prove, and our proof is complete. My apologies for the dogs in the background. Our next statement is a little bit more difficult to prove. Not by a lot, but we have to use some previous results in our proof. We cannot simply rely on our assumption and the definition itself. The statement says if x is any integer and if 2 is a divisor of the expression x squared minus 1, then 4 will also be a divisor of the same expression. We are going to prove this one directly again. So we are going to take the hypothesis, the if part, and we are going to assume this is true. And then we are going to try and show that if this is true, then the consequent, the 4 divides x squared minus 1, will also be true, or it will naturally follow from the assumption. So let's start our proof. Let's say here at the top, we always start by setting our scene. Let x be some integer, and we are going to assume that 2 is a divisor of x squared minus 1. Again, we have a definition to describe what this means. So here we can just expand a little bit on that. This means that we can take x squared minus 1 and we can write it as a product of integers, where 2 is one of the factors. So let's say we can write it as 2 times m, where m is some integer. If we think again about the parity of this, if something can be written as a product where one of the factors is 2, it actually means that expression is even. We are going to use this fact in our proof. So x squared minus 1, the expression that we are looking at, is an even number. We are going to try and show that it's not only even, it's also going to be a multiple of 4 as well. All right, so how do we do that? What we are going to do is take this equation and solve it for x squared. If we take the negative 1 over to the other side, we get x squared is equal to 2m plus 1. And in fact, this is our definition of an odd number, right? It is a multiple of 2 with 1 added to it. So this means, therefore, x squared is odd. What do we do with this information? We already have the definition of what it means to be odd. This is what we can deduce from that definition. How can we use this in our proof? Well, we cannot go any further than this if we don't use other previous results. Now, there's a result that states the following, and I'm going to write it here on the left-hand side. It says, if x is an integer, we have the following. X squared is odd if and only if x is odd. Another way of writing this is to say that if an integer squared is even, this will be true if and only if the integer that is being squared is even itself. So what we can take from this result is the fact that we have an x squared being odd. This is what we found from our definition or from our assumption. So if we take this, this is going to apply or imply that x itself is odd. And we have a definition for what it means if x is odd. It means we can write x as 2 times some integer plus 1. So let's say it's 2k plus 1, where k is an integer. This is the crucial part of the proof. Without this, we couldn't really go much further. Now, what do we want to do? We want to take a look at this expression, x squared minus 1. We want to describe it with the information that we have, and we want to show that if we do this, we have a common factor of 4. So if we replace our x squared by 2k plus 1 squared in this expression, what does it give us? Well, 2k squared gives us 4k squared, plus that middle term, 2k times 2 is 4k, plus 1 minus 1. Can you see there exactly is what we want. We have our factor of 4, which we can factorize out. And what is left, k squared plus k, this is obviously also an integer. My space is a little bit restricted here, but what this means, finally, we can make the deduction that 4 is indeed a divisor of x squared minus 1, and our proof is complete. I just want to recap again what we did here. What we started with was the assumption that x squared minus 1 is divisible by 2, or x squared minus 1 is actually an even number. We solved this equation for x squared and saw that x squared is in the form of an odd integer. Then we used this result. If x squared is odd, it means x must be odd as well. If x is odd, we have a definition for what that means. It must be written in the form 2 times some integer. We use a different k here just to be as general as possible, plus 1. Then we take this new x. We plug it back into our expression, the one that we want to investigate. X squared minus 1 boils down to this, 4k squared plus 4k. And there's that common factor. We wanted to show that 4 will always be a factor of this expression, and that's exactly what we did. All of the statements that we've proven so far have been done using direct proofs, meaning we assume the hypothesis is true and we show that the result or the consequent follows naturally from our assumption. For this statement, a proof by contrapositive would be easier. The statement says let x and y be any integers, and it says then if 3 is not a divisor of xy, then 3 will not be a divisor of x, and 3 will not be a divisor of y. We have a nice direct definition of what it means for an integer to be a divisor. We don't have a direct way of describing what it means for an integer like 3 not being a divisor of xy, or of x and of y. So what we are going to do is we are going to use the contrapositive. Now, if we have an implication like if P then Q, we know this is logically equivalent to the contrapositive. If not Q, then not P. And this is what we are going to use in this statement. So let's just rewrite using the contrapositive. This will say if 3 is a divisor of x, or if 3 is a divisor of y, then 3 will be a divisor of their product, xy. Just take note of this. The consequent for us was this. It was a conjunction. 3 is not a divisor of x, and 3 is not a divisor of y. When we negate this, we are negating everything, and we are actually applying De Morgan. We are saying the negation will be 3 is a divisor of x. When we negate and a conjunction, it becomes a disjunction, an or. 3 divides y. So this is actually very important in our assumption. Otherwise, the statement that we are proving is not equivalent to the original statement. All right, so let's start our proof. We are going to let x and y be integers, and we are going to assume the following. Now, our hypothesis says if 3 divides x or 3 divides y, we can assume any one of these two because it's a disjunction. So let's assume 3 divides x. Right. What does it mean? This means we can write x as a product of two integers where 3 is one of the factors. So let's say x is equal to 3m, where m is an integer. We would like to show that 3 is a divisor of the product xy. So if we take a look at what xy is, xy will be x, which is 3m, times y, We would just like to show that 3 is one of the factors of this expression, and it is. We can just rewrite this, 3 times my, and the my in brackets is also an integer. So therefore, we can show very quickly and very directly 3 will be a factor, or 3 will be a divisor of xy, and our proof is complete. We don't need to look at the case where 3 is a divisor of y as well, because the hypothesis was a disjunction. It says if 3 is a divisor of x, or if 3 is a divisor of y, then we will have this. So you could have assumed 3 is a divisor of y and shown this, or we could have done it the way we did, meaning assuming 3 is a divisor of x only. It doesn't require both of them to be true at the same time. So this proof, although I know a lot of students will feel like it's only half of a proof, where is this part? You could have used this part instead of this part in your assumption, but we don't need both to be true at the same time. We can only use, or we are allowed to only assume one at a time and still show that the result holds. For our final proof, we are also going to be doing a proof by contrapositive. The statement says, let x be any integer. If 3 does not divide x squared minus 1, then 3 will divide x. So we are going to rewrite this first of all again. If 3 does not divide x squared minus 1, then 3 divides x. This is equivalent to proving if 3 does not divide x, then 3 will divide x squared minus 1. This is the contrapositive. All right, so let's start with our proof. We are going to say let x be an integer, and we are going to assume 3 does not divide x. We don't have a direct way of describing what this means. The closest we could come to this is to say, well, if this is the case, we cannot write x as a product where 3 is one of the factors. This is the closest we could get to what this actually means using a definition. But let's look at the number line. What does it actually mean if it is a multiple of 3, or if 3 is a divisor? I'm going to use the line here right at the bottom. Let's say we have all the multiples of 3. So 0, 3, 6, 9, etc. And here to the left, we have the negative multiples, -3, -6, -9, and so on. We are looking at all the integers that are not these. So I'm going to fill some of them in. And I'm going to use color here, and hopefully it makes a little bit more sense. We have 1 larger than a multiple of 3. So let's look at 1, 4, 7, 10. Over here to the left, we have -2, we have -5. So these are definitely not divisible by 3, but they are close to multiples of 3. And let's use purple for the other ones. Let's say 2, 5, 8, 11. The pattern here is that these numbers in purple that I'm writing down are always 2 integers larger than a multiple of 3. Okay, so we have 2 cases of what we are dealing with. I'm going to highlight these ones first of all. So the 1, the 4, the 7, the 10. Let's describe them. And I'm just going to make a little space here for us. If we have that x is in this form, so 3m plus 1, where m is an integer, we get all of these values, the 1, the 4, the 7, the 10. These are all the integers that are just one larger than a multiple of 3. This is one of the cases that we are going to look at in our proof. For the next one, we take a look at these ones, like the 2, the 5, the 8, and the 11. How can we describe these ones? Well, we can say in this case, it's a multiple of 3 plus 2. This covers all of the integers in between the multiples of 3. So we are going to take a look at both of these cases. Since we have that x is not equal to 3m, in our proof, we are going to assume, or we can say this is, x will then either be of the form 3m plus 1, where m is an integer, or x will be of the form 3m plus 2, where m is an integer. We simply need to take a look at both of these cases to try and show that 3 will be a divisor of x squared minus 1. So let's take a look at the first case. Right? If this is the case, let's evaluate x squared minus 1. If we replace x squared by 3m plus 1 squared, and we expand this, we get 9m squared plus 6m plus 1 minus 1. And if we simplify this, we want to show that 3 is a common factor, but there is a common factor of 3 that we can remove. If we factorize this out, we will get 3m squared plus 2m, and what we have in the bracket, 3m squared plus 2m, is indeed an integer. So what this means is 3 is a divisor of x squared minus 1. In the second case, if we take a look at x squared minus 1, but we use the second form, 3m plus 2, let's expand this. This is going to give us 9m squared. We will get 3m times 2, which is 6m times 2, which gives us plus 12m, plus 4 minus 1. Again, we end up with a common factor of 3. If we factorize it out, we get 3m squared plus 4m plus 1. And 3m squared plus 4m plus 1 is also an integer. So my space is a little bit finished here, but in both cases, we have shown that 3 is a divisor of x squared minus 1, which is exactly what we wanted to show in our proof by contrapositive. This is what we wanted to end up with. So our proof is complete.